Okay. And right before I start, I just want to show you guys really quick. If you look at the right side of your, there should be like a little bar right here. There's going to be a hand icon and a question bar. If you guys have any questions at all throughout the session or at the end of the session, or if you run into any errors, feel free to raise the hand icon or just submit your questions, and we will get to you as soon as we can. We have our team on here as well. And if you have any questions for Amir, we will leave those for the end after he's done with his presentation. Okay, so yeah, so now without further ado, we have Amir. Amir is a senior structural bridge engineer. He currently works at Stantec with more than 12 years of academic and professional experience in the civil engineering industry with a particular emphasis on construction structures and bridges. He is skilled in finite element analysis, computer-aided design, earthquake engineering, and he has a doctorate of philosophy with a focus on structural engineering from North Carolina State University. And he's also a member of the Precast Pre-Stressed Concrete Institute for many years and has participated in many of the PCI research projects. He is the recipient of the 2018 T.Y. Lin Award for his outstanding research on pre-stressed concrete thin-stemmed members depth ends. So I think, Amir, if you can just give yourself a brief introduction whenever you are ready, and we can get started.
All right. Well, thanks, Lucy, for the introduction. And I'm really enjoying to be here today with every one of you and go over this topic for the construction stage analysis in bridges. I personally enjoy this topic. This is one of the most interesting topics in bridge engineering. And I personally enjoy it very much. I learn a lot about it every day. There is no single problem or bridge or model that is similar to the other. Every time you learn new things about it. So I consider myself fortunate today to be here and try to get some introduction to this interesting topic to you all. So today I'm going to cover some models that are employing the construction staged analysis, and those models represent different levels of complexity in bridges. So I would like to start with the basic models for those who are introduced to the topic, and then later on I'm going to switch gradually to more complex models. So this way we can introduce the topic in a nice and neat way, and in the same time simple way. And the concept, at the end of the day, the concept is close in all models. The level of complexity or sophistication differs definitely according to the type of the bridge or the system that we are analyzing. So I prefer always to show the screen on MIDAS right away and explain things on models. I feel that this is a better way to convey the idea, or that's the way at least that I do it. I like to do it. So I'm gonna start first with the most common bridge that we see in United States every day, and every one of us, or whoever of you who is working in a design firm for bridges or something, is going to be introduced to the precast, pre-stressed concrete girder bridges. So this type of bridge is very simple. It consists of a precast girder that can has any shape, can be an I-shaped girder or U-shaped girder. And basically you have the deck that's casted on top of it. And at some point, the deck and the girder form together a composite section, which means they are completely bonded together and there is no slip between the girder and the deck at the top. So this is one of the very popular bridge systems here for the accelerated construction and for the cost. It's a structurally efficient system as well. So I'm just going to introduce quickly a simple model here to convey the idea of the construction staged analysis. So Whenever you start the model, you are going to go over the tree here that MIDAS present, which is a systematic and a logical way to present a finite element model. Definitely you have your material definition. I'm not going to spend time on that because that is very basic, just defining the materials of the bridge or the materials for the different components of the bridge. Just simply here, we have the precast girders that will require a high-grade concrete material like 8.5 KSI or higher, and you have the concrete material for the deck, the intermediate diaphragms, and the end diaphragms. Then I do have a material here that I define. It's called dummy concrete material, and this material is not a physical, realistic material that is used in the bridge, but it is just a way of defining something in finite element, just to that I'm going to go over it later in the construction staged analysis. So this material is basically very close to a concrete material of 4,000 PSI strength, but the only difference that I'm setting is 0 here for the density or the weight. So this way, this material does not have any weight. And I'm going to describe just shortly why I have to define a material like this in the model. Then finally, you will have the material for the pre-stressing strains, which is typically 270 KSI grade steel, low relaxation steel. So the material definition is kind of a basic thing in any finite element model and is a very important thing, the properties of the material properties, because they affect the analysis right away. Then you switch to defining all the sections for all the different components of the bridge, including the longitudinal girders, which are the main elements carrying the bridge. You have the intermediate diaphragm, the exterior diaphragm. So just to go over this with you quickly. So here in the section definition, MIDAS actually have a nice library, very comprehensive one, that includes all different types of sections that you can be exposed to in bridges. So here, for example, you can see all different types. You can pick whatever section you need and just go ahead and define all the dimensions and hit on calculate section properties. So it automatically calculates the area, the product, the moment of inertia about the two primary axes of the section, and shear area, and all the different properties of the section here. So for this particular model that I'm talking about, I am having a bridge here. I'm going to show you the cross-section of the bridge. So this bridge is consisting of 4 girders, like you can see. Those are bulb T78 girders, and we have the deck that's casted on top of them. So we will have to define the properties for this section, the bulb T78. And to do this, if you go under the section tab, you would select the pre-stressed concrete section option, which is available in here. Pre-stressed concrete section property, and then you have here all the different shapes that you can select. So the bulb T78 is an eye girder shape, so you will select this one, and definitely will go over this schematic here that shows you all the different dimensions that you need to input, and you give a name for your section, and that's how you define your bulb T section, which is the section for the precast concrete girder of the bridge. Then I do have here a definition for the interior girder and definitions for the 2 exterior girders for the bridge. So the interior girder, you can see this is a composite girder now. It's consisting of 2 parts. Part number 1 is the precast concrete girder, which is the bulb T78. Part number 2 is the deck section on top. So the nice thing here is the option that you can define a composite section right away. If you go over this tab here and you hit composite, so this gives you an option here that you can select the type of the composite section that you are looking for. So this is a composite eye girder section, and you have to define the parameters for the slab, which means the effective width of the slab that's working with the girder, thickness of the slab, and any haunch thickness that you are interested to define in here. And then later on, you can go here and define all the different, based on this schematic here, all the different dimensions for the precast girder as well. So this way, you end up defining a composite section that's constituting of those two parts, the precast girder and the slab. So that's a very direct way of defining a composite section. This can be a composite I section, T section, or a composite pre-stressed girder section. And this option here is an interesting one because you only define the properties for the slab and you can import your pre-stressed concrete girder section right away from here. But this requires one step before coming to this window, is to define your precast section first from that tab over here. So if you come here and select or define any precast concrete girder section from here, and it's going to be saved in the sections, you can later on pick it when you define the property for the composite section just by selecting this option here. There is also a nice option for a composite general section, and this option can enable you to import any section of any shape. In case if you have any irregularities of the shape or something, you can always draw any section with any dimensions or any configuration, and you can draw it on AutoCAD in DXF format and then import this section file later on. And this is one of the interesting things in this model. So beside the interior girder section, which is this one, here I do have this right girder and this left girder here. You see clearly that the girder is not centered with the deck. This is because of the geometry, the overhang and the spacing here. So in order to create a shape like this in MIDAS, you definitely need to, the easiest way to do it is to go to AutoCAD and draw all the dimensions of the section here, everything to scale for the precast girder and the deck on top of it in the CAD file, and just save it as DXF. And there is a nice tool here associated with MIDAS. It's called Section Property Calculator. And this property calculator is like a small software or program where you can pick your units and define the materials here for the two pieces of the section, and you end up creating the section like this. So this is a way that you just need to define the material for the two parts, the concrete girder and the deck, and you can generate a composite section from here, define two parts here, and the base material is the material for the precast section. And then through those steps here, you can complete the steps to calculate or to create your composite section right here. And the nice thing about this, that you can also calculate all the properties for the composite section. It is a very simple thing. You select a mesh size. So all what happens is that the section is kind of discretized or is divided into elements that are sized every 1.5 inches. And then MIDAS automatically calculates the properties for part number 1, which is the precast girder, and part number 2, the slab, and then the two parts as composite together. And you can easily see the composite property here, or the table here. This table provides you with all the properties that are calculated for the girder part, or for the deck part, or for the composite section altogether. So all those different tools that are provided in MIDAS help you at the end of the day to define all different geometries for different sections, interior ones, exterior ones, ones with regular section geometry, ones with irregular geometries. All of those ones can be defined very easily and systematically in the program. Also for the intermediate diaphragms, those are very simple sections because they are rectangular shaped or T-shaped sections like this. So we can just use the library right away to define the intermediate diaphragms, the end diaphragms. And this way we end up having the materials and the sections completed. Then the next step before going to this will be to define the geometry of the bridge. And of course you have here the node element tab. This is a big tab that has different options here that you can create nodes using coordinates. You can copy or translate or move the nodes around. You can merge nodes together. So this is a neat way that you can start creating the main or the primary nodes of the model, and then you can connect the nodes together with elements to create the frame elements or the beam elements for the girders and the beam elements for the deck. This model, by the way, is a grillage model. So this is utilizing beam elements for all components of the bridge. So we are utilizing beam elements for the main precast, pre-stressed girders here, and we also have beam elements for the deck elements that are connecting those longitudinal members together. We have beam elements for the intermediate diaphragms and for the end diaphragms as well. So one nice way that you can define geometries also whenever you have an irregular geometry or kind of complicated one like this one that I'm showing on the screen. For example, this is one single span of a main line of a long bridge. It's just simply a supported span, and we have two spans that are framing into this span, an on-ramp and off-ramp spans that are framing inside the main span here. So a complicated geometry like this, so the easiest and best way to do it will be to jump to AutoCAD and draw all your beam elements neatly and easily in AutoCAD. And all what you need to do is to define different layers or levels, which represent the different components. Like the deck elements will be in a group or a level or a layer. And you have a group for stringers, a group for diaphragms, a group for cross girders, everything in a separate layer. And whenever you get to MIDAS here, you can import this DXF file very easily using this option here, and automatically all the layers are transferred inside MIDAS into groups, what we call as groups. They will fall in here with the same names. So later on, you can pick any group. If you hit or double click on it, it can highlight the elements that are included inside this group. I'm going to talk about these groups just in 5 minutes or something, because this is a very primary thing for construction staged analysis. But I just wanted to go through or over the main or the key components of the model. Definitely you will have your boundary conditions, which means the support conditions for the girders. So in here, I modeled the bearings here as nodes, and I do have like rigid links that are connecting the top node of the beam of the girder with the node that represent the bearing down here. This rigid link represents the depth or the height of the girder, as this element here, or this frame element or beam element, is meant to be at the top center of the girder. So this represents the top of the girder here, and that's why this rigid link is representing the depth of the girder. Then at the bottom nodes here, we go and start defining our boundary conditions. So typically for those bridges, you are using elastomeric bearings or any type of neoprene bearings. So you end up defining the properties for the bearings in terms of the stiffnesses for the different degrees of freedom, and that's how you define the boundary conditions for the bridge. Then jumping to the loads, you start defining separate load cases for all the loads that are included in the model, starting with the self-weight, which is automatically calculated by MIDAS for any component that has a material and has a density or a material defined and the geometry with dimensions. MIDAS is going to automatically calculate the self-weight of this component if you define self-weight in here. I herein define the weight for the haunch and the stay in place forms and the deck, the weight of the concrete of the deck. And this represents when we install or erect the girders on the columns. And later on, we come and install our stay in place forms and start pouring the deck. So the weight of the fresh concrete is acting on the precast section only. It's acting on the girder section only. It's not acting on the composite section because it's not composite yet. So this load should go to the, or should actually act on the girder section only. So that's why I calculated the load here for the stay in place forms, the haunch, and the deck. I added this load as a uniformly distributed load on the beams or the girder elements in here, and I added this in a separate load case. Then I have a load case to represent the pre-stressing tendons or the pre-stressing strands. Those are pre-tensioned elements, so all those pre-stressing tendons that I'm using are just lumping the strands together, all the strands together in a resultant strand that has the resultant area of the pre-stressing strands and the force as well. And also finally defining the barrier weight, which is defined as uniform distributed load. And the nice feature about this also is that MIDAS enable you to put the load in on along its line of action. So since this load is eccentric with respect to the girder here, so we are applying this load in their location with some eccentricity from the exterior frames or the exterior beams. So this tab is defining the tendon property, which means the cross-section of the strands and the materials for the strands, and finally the tendon profile, which is basically the when I displayed the tendons here, It is basically the profile of the tendon is showing that we have one straight tendon and one hard tendon like this. So this is just defining the tendons, and this is a basic thing for bridge models. And finally, you can also define your moving load case, which consists of those steps, defining the lanes where the traffic is going. On top of the bridge, define the type of vehicles that you are dealing with. For example, for this particular model, I'm showing the HL93 tandem and truck loading, and defining the different moving load cases, which means that you start defining. So for example, for this bridge, we have 3 lanes. We can say that we have a case when we have the 3 lanes all loaded, or first 2 lanes are loaded, or the last 2 lanes are loaded, or you can have a case that represents all different cases or situations. When you choose to pick here, when you define the moving load case, you can simply pick here that you want to have a particular number of lanes that's loaded. Like for example, for this case, I'm loading all the 3 lanes with the load. Or you can have a case like this where you define to MIDAS or ask MIDAS to try all different possibilities, such that the minimum number of loaded lanes is 1 and the maximum number of loaded lanes is 3. So this means that MIDAS is going to go over all the different possibilities of loading the 3 lanes together, or any 2 lanes at the same time, or a single lane at one time. So this, up to here, these are all the basic steps for defining any finite element model for bridges. So now I'm going to focus more on the construction stage analysis, which are why we are here today. So let me start to explain the construction stage analysis window here. So in order to start this analysis, the basic step that needs to be completed prior to going to the construction stage analysis window is to define your groups. And MIDAS has 3 different types of groups, either a structural group, or a boundary group, or a load group, or a tendon group. Those are 4 different groups, but they consolidate into 3, as I'm going to mention later on. So the structural group means that you are basically selecting all the elements that will appear as one group. Like for example, here I have all the girders are selected and placed inside one group. Then for the cross deck, like all the elements that are representing the deck elements on the top of the bridge are placed in one group. I have a group for the intermediate diaphragm. I have a group for the end diaphragms. And I have one group here that combines both the deck elements and the diaphragms together. And the idea of having groups like this is that later on, when you go to construction stages, you need to clearly identify in each stage which group of elements is going to be active. And that's how MIDAS starts to understand the construction sequence of the bridge. Like, for example, I'm going to start first erecting my girders. So I need to get the main girder group to be active in the first stage. Then later on, when I come to the stage that the deck is poured and started to harden and we are getting into composite action, I can go ahead and activate this group that has the cross deck elements. Also, the same thing that applies to the structural groups applies to the loads. You need to define every load case that you have in the model in a separate group here. So you will see clearly I'm having the self-weighting group. The pre-stressing tendons are applied in a load group, the deck weight in load group, the barrier load in a group, and any other load case that you are interested in, you have to define it in load group. Because later on, you can, at a particular stage, activate a load group, which means that you are saying that this load is going to be simply activated, active, or applied at this particular group. And the same thing also applies for the boundary condition, which means that you are saying, for the first case, I'm going to, for the first stage, I'm going to activate the main girders, and I'm going to activate the bearings as well. So this way, the MIDAS understands that the girders are supported on the bearings inside this stage. So if you go to the construction stage analysis, that's how it is presented by the program. So you can create as many stages as you want here. And the idea is that you create a stage, you give the stage a name. So for example, this stage is consisting only of the bulb T78 girders, which is the precast section only of the girders. So the way that MIDAS handles the construction stages is that it's going to ask you on 3 elements. What are the elements that need to be active or deactivated in this group? And what are the boundary conditions that you want to activate or deactivate in the group? And similarly, what are the loads that are going to be active or deactive in the group? So that's how the program understands the sequence of the construction. So for example, for this bridge, I am putting all the girders in this group that's titled main girder. So I'm going to activate the main girder group. That's the structural element group that's active in this stage. For the boundary conditions, I need to activate the bearings. Otherwise, the girders are not supported on anything. So I need to make sure to activate all the rigid links and the bearings to make sure all the support conditions are active. And whatever load that needs to be applied in this stage, for example, the self-weight of the girders needs to be applied. So this also needs to be activated. So we have the stage number 1 when we have the bulb T78 girders active. Then going to stage number 2, I'm just activating the pre-stressing strands. So just simply, there are no elements that are active. We are just activating the pre-stressing effect, and the pre-stressing effect here appears under a load group. So the pre-stressing effect on the structure is just simply the pre-stressing force applied on the girders. So it's just a load group, not more than that. You are not actually activating elements, you are activating the load coming from the pre-stressing. So that's why this appears under load. You will find the pre-stressing load group here is active in this stage. You don't have any boundary conditions or elements that are active. Then we come, and this sequence here reflects how the bridge is constructed. So you have your girders with their pre-stressing in the first stage, and then you come to a stage where you pour the deck. So when you pour the deck, this means that you have installed the stay in place forms, and you are pouring the deck, including the haunch or the build-up thickness and the deck on top of it, and the intermediate and the diaphragm and the exterior or the end diaphragms. So all this is only applied in this stage as a load, because all this is applied as a load on the precast girder section only. So the bridge is not yet composite because we are still pouring the deck. So the weight of the fresh concrete of the deck and the haunch is only applied on the non-composite section or the pre-stressed girder section. So this stage only consists of a load that's active, no boundary conditions and no elements. Then after you pour the deck, you will definitely arrive at the deck to the stage that the deck is now hardened. So the composite action kicks in and the stiffness of the deck starts to kick in inside the problem, which means that now the girders became composite sections. And to activate this, or to make the software understand this, we activate all the groups that consists of the transverse elements. So those are all the deck elements, which are the beam elements connecting the girders in the transverse direction. And in addition to the intermediate diaphragms and the end diaphragms, all those elements need to be activated in this particular group. No boundary conditions are added or no loads are added. And the reason why no loads are added in this group, because the weight of the deck and the diaphragms and the build-up or the stay, the haunch and the stay in place forms, all of those loads were actually included in the previous stage as a load here on the deck. So whenever we come to this stage, we are only activating the elements, which means that the stiffness of the deck is the thing that comes into place, but there is no additional weight added inside this stage. And this now answers the question why I earlier defined a material that's called dummy concrete. It's a concrete material similar to the deck material, but it does not have any weight, because actually I'm defining all the deck elements here using this material. By the way, in MIDAS, if you click on any material or any section, it automatically highlights all the elements that are assigned to this material or assigned to this section. So if I click on dummy concrete, it shows me all the deck elements here are highlighted. So those elements are having a material that reflects the stiffness but does not include weight. So whenever those becomes active in the composite stage here, this means that no weight is added to the model, it's just the stiffness that is active. Then going back to the construction analysis, after composite girder, we have one stage that I have here that I included the barrier load, and those are all, this represents all the loads that come after the section is composite or after the bridge is in the composite stage. So this includes barrier loads, wearing cores, or any loads that will be added later to the structure. So this is just a load that's active in here. We don't have any elements or boundary conditions. So the important question here is basically for the girder definition. Yeah, so also one thing that if you activate this icon here, it can show you an extruded view for the elements that are active in each stage. So this means bulb T78, you only have the girders active here. Then if you go to pre-stressing, it's going to show you the tendons are added in this stage. Then you go to deck weight, it's not going to show any elements because we only have the uniform load that's applied from the fresh concrete that's poured and the stay in place forms and the diaphragms. And then later on, if you go to composite, this is going to show all the elements active for the deck, the intermediate diaphragms and the end diaphragms. So now you can see the solid ends here because of the end diaphragms. And finally, if you go to the barrier load, it's going to show you the load that's applied for the barrier. So one key question here, when we defined the section for the girder, remember we had the bulb T78 section for the pre-stressed section. Or the pre-stressed girder, and then we defined here the composite section for the interior girder. This section was showing two parts, part number one for the girder, part number two for the deck. So how does MIDAS understand that part number one is active in the first stage, which is the bulb T78, and part number two starts to be active in the composite stage? And the reason why I'm mentioning this, because here I define this group as main girders. This group includes the interior girder and the exterior left and right girders, which are actually now composite girders or composite sections. So whenever I come here to the construction stage analysis, the first stage, I asked to activate the main girder. So now activating the main girder is going to activate the entire section, including the two parts, part number one and part number two. So how can I make the program understand that I just want part number one only to be active in this stage because we are still, we have not poured the deck yet. So to do this, MIDAS has a nice feature here. It's called composite section for construction stage. And this is a particular window that is built to define how the composite section, whenever you have any composite section defined in the model, for example, for the interior one or the exterior girders, you can identify that you have part number one and part number two. Part number one is the girder. This is the one that's having the material for the pre-stressed girder. And this one you can easily identify here that this is going to be active in this stage. So the stage that's going to be active is bulb T78, which is the first stage. And then later on, part number two, which is this deck, which has the dummy concrete material, this is going to be active in the composite stage. So this way, MIDAS creates like, it divides the section into two parts, and you can determine which part needs to be identified, needs to be active in which stage. So this way we can have part number one active in the first stage, part number two active in the composite stage. So we do this same definition for all the sections that are defined in the model that are composite. So this way we come to this conclusion whenever we activate part number one or the first stage, it's only showing you part number one. It's not showing part number two. And that is the only case or the only element that's active in this stage. Just switching to a second model very quick. So I'm not going to go over all the details that I described in the previous models, just to make it simple, but just go on the tips or the things that are different inside this model. So for the people who prefer to use the plate element or the shell element for defining the deck, this is a model that represents a plate element model. So here I'm basically defining all the girder sections using the frame element or the beam element as usual. And this bridge, by the way, is using the U-girder shape, which is a very popular shape that's used in many states now. And basically for the deck elements, I basically defined all the deck elements using shell elements or plate elements. And that is the idea, because the plate element provide some different distribution as compared to the grillage element. So each element can provide differences in the distribution of the loads in the transverse direction. So whenever you have a case like this, you can still model your girders using beam elements, still model the deck using shell elements, and you can go over all the steps of the model as the same like the previous model. And the only difference will be whenever you come to the construction stages, you define all your stages normally, the same way like what we discussed. And I will go very quickly on them with you. This is the first stage when you have the U-girder section active. Then second stage, I activated the pre-stressing force. Third stage, I'm just applying a uniform load on the girders for the deck pour. Fourth stage, this is where I activated the deck elements. And don't forget that the deck elements, I'm defining a dummy material here for the deck elements to make sure that those elements are just activated as a stiffness inside the model, but they are not activated as a weight, since the weight was already included in the previous stage. And finally, you can add barrier or any other load cases that will be added on later on. So the difference comes now when we display the results in the models that are utilizing the plate element. How can we make sure the bending moments that are shown on the girders, are they shown on the beam element only, or are they shown on the plate element, or there is a way that we can show the moment on the composite section, which is now included of the beam elements and the plate elements associated with it. So in order to resolve this question, so what we do easily is that we create 3 groups. For example, for this particular model, we had 3 girders. So we have a group for each girder, and this group is going to consist of all the beam elements for the girder and also the deck elements, the effective width of the deck that's associated with this beam. So this way we are combining the beam elements and the deck elements together in one group. And then later on, after we run the analysis, there is a way or an option here when you display the results. Instead of going to beam diagrams is going to show you the bending moments on the beam elements only, but you can now show the resultant force diagram, and the resultant force diagram shows you the bending moment on the composite section, which means the deck and the beam element together. So I guess I just need to remove the extrusion here, and you can select the load case that, for example, if I'm looking for the live load moment, I can pick whatever case for the live load and just hit apply and show the values. And of course, make sure that you are selecting the convenient decimal points or precision and the convenient units here, and you can read the moments on the composite section. So this section now includes both the plate element and the beam element. If you go and display the moments here on the beam diagram instead of the resultant force diagram for the same load case and everything is the same, this is going to show you the moment on the beam element only. And by the way, the moment that was shown on the resultant section, it is just shown on the compression side, but that doesn't mean that the moment is reversed or anything. The moment, the tension side is still the bottom fiber of the girder, but it is just represented this way. So I'm going to go over the third model. I think we will still have 12 minutes. We can go over that one, just to represent a level of complexity in those bridges. So this example here is for a continuous steel plate girder bridge. And this is a 4 continuous span steel plate girder bridge, like you can see. This bridge is a bridge that was crossing the I-10, Interstate 10. And you can imagine the I-10 is a very primary route in all the interstates, definitely, in United States are very primary routes. And this bridge actually is consisting just to give you an idea of the main system of the bridge, this bridge is consisting of 2 longitudinal steel plate girders, and those are curved plate girders, like you can see here. Those are the main supporting elements of the bridge. So this bridge is consisting of only 2 curved steel plate girders that are supporting floor beams in the transverse directions, and the floor beams are then supporting the deck. So if we look at the groups for this model, you basically have all those groups represent the groups for the girder, the steel plate girders, the 2 steel plate girders. We have a group that represent all the deck elements. and we have a group that represent the floor beams as well in the bridge. Just to show an extruded view, this is how it look like. Those are the two plate girders. There are two primary main supporting elements for the bridge, and there are a bunch of cross beams or floor beams that are crossing and supported on those two girders here. And then we have a group of elements that represent the deck. This is a grillage model. And this is a 4-span continuous bridge, like you can see. And the problem with this bridge, or the interesting problem, was that the bridge got hit here because we have the I-10 here, and the bridge got hit with a freight truck that was high enough to damage the bottom flange of one of the plate girders, of the steel plate girders. And because of this damage, it was required to kind of replace the girder in order to solve the problem. There was no way that we can heat straighten the girder or employ any other technique in place to do it because of the damage that was very extensive on the girder. So we ended up deciding to replace the plate girder or the beam. And of course, this was the only span that was affected by the damage. So this means that we don't need to replace the other 3 spans. So you are looking at removing a portion of the girder here and replacing it with an intact one. So that was the complexity of the problem. How can we come to a span like this, take a portion of the girder out, and we need to employ an effective construction sequence to make sure no other element in the bridge is going to be distressed during this operation. And the adopted or the chosen repair procedure consisted of demolishing the deck. We need to remove all the elements that are supported on the damaged girder first. So demolishing the deck in this portion here and taking out the floor beams or disconnecting them from the system, and then disconnecting the damaged section of the girder from the splice to the splice, because those are the locations where you can disconnect the girder from. And of course, we cannot disconnect one girder and leave the other one. So there is no point about that for the stability of the bridge or the system of the bridge. So the idea is to remove the 2 girders together. So this is a very efficient, effective model that shows the importance of having construction staged analysis in bridges because of the 3 aspects: the indeterminacy of the bridge, it's a continuous system, so it's kind of sophisticated in terms of the structural analysis of the bridge, and how to predict the response of the structure throughout all phases of construction, or the different phases of construction, and how to make sure whenever we go on this repair scheme, we are not going to distress any other component in the bridge. So the idea here was to create groups for the elements that are going to be removed. So if we go over the construction stages here, of course, we developed a full model for the bridge that has all the girders, the floor beams, the deck, all the loads that are in service acting on the bridge, with exception of the live load, because the bridge is now closed for repair. So we don't have any live load going on top of the bridge. So we defined a full model, including everything. And this was the first stage whenever you have the bridge in service under operation, but only under dead loads. And the repair scheme consisted of applying a temporary support first to the adjacent spans. And those particular selected locations. So you see the nodes that are highlighted here. So this represents temporary shorings or shoring towers that were installed underneath the bridge at those particular points here, because later on in the coming stage, when we go ahead and start demolition of the deck and taking out the floor beams and removal of the girders, this is expected to transform the system of the bridge from a full span to 2 cantilevers, one cantilever extending from this side and the other from that side. So of course, the bridge was not originally designed for that. So the cantilevers are expected to have an upward deflection because of releasing the load or removing the load from them of this portion here. So of course, having those tips of the cantilevers going up will push on the adjacent spans downwards and will increase the positive moment on those 2 adjacent spans downwards. So in order to control the deformation or the deflection, the upward deflection at the tips of the cantilever here, we need to provide some temporary support or shoring at those points such that those points are supported. So this way we can control the upward deflection of the cantilever. So at this stage, this is an example of a stage that I'm just applying a boundary condition only. That's not applying any loads. If you look at temporary support, I'm just activating here a temporary support representing shoring towers or something that are only supporting those points in the vertical direction. That's all. And then when you shift to the span removal stage, this is where we are taking out the deck, demolition of the deck, disassembling or disconnecting all the floor beams in the portion of the girder that needs to be replaced, and disassembling the portion of the plate girder, the left one that had the damage, which was this one here. And these are disassembled from the splice to the splice. And the other girder that was not as damaged as the first one as well. So now the system, you can see, is transformed into two disconnected pieces, a span with the cantilever and two spans with the cantilever. So this is a major change in the system of the structure, and that's why construction stage analysis importance is very significant here, where you can see how the response of the structure changes in each construction stage and how to predict what upward deflection will happen at those points. The main aspect that I'm talking about this upward deflection at those particular points, because later on when you get the new girder and install it on this bridge, you want to make sure the tips of the two girders are on the same level. Otherwise, it's going to be impossible to install it or erect it. So you need to have full control of the deflection at those ends here and here. And in order to do so, there were two techniques that were adopted in this project. One of them was not only supporting those with the shoring towers, but rather having jacks installed on top of the shoring towers that can jack against the girders. So this way we are pushing here up to make sure those points go down and until they get leveled together. And the other technique beside jacking up was to apply additional loads or additional weights. And those loads came in this stage later on. Then we go and apply some sandbags at the ends here, at the tips of the cantilever, to make sure that we level the points. And when they come to install the girder, we end up with the two tips leveled, so it's easy for the contractor to come and install this girder. You see, this problem is sophisticated because it is a statically indeterminate structure, and you are also removing part of the span, so you are changing the statical system of the structure. So we ended up having different loads at each tip. A problem like this, it is really difficult to solve it by hand. You cannot do that. It's very important to use finite element analysis for that. And of course, employing the construction stages is very important to predict the response of the structure accurately. One thing, if you are interested to see how the bending moments change in different construction stages, I'm just running this. It's not going to take a minute. So you see here, you can always go to the first stage when we had all the service loads applied, and you can display the bending moments on the girders, the steel girders. Of course, here when you display the results, you can show only all the dead loads in the structure or show summation. If you choose summation option, this gives you the summation of all the moments, including pre-stressing, dead loads, all different loads together. And we can show this even as a shape for now. So you see, I'm going to just switch off the loads to make sure that you see clearly the bending moment shape. So this is when the bridge is under operation in service. You can see clearly the continuous moment shape for the continuous curved steel plate girders. And then you go and apply temporary supports at those points. At this point, the structure is already deformed, so we are just applying shoring towers that are not even touching. They are very close to the girder, but not touching the girder, so we have not really changed much in the statical system yet. But later on, when you apply the span removal, this is where you took out the portion of the damaged spans here, and you transformed your statical system to cantilevers, you can see clearly the negative moment here, and the moment shape here is interrupted because of having the temporary shores or supports that were placed right at this end. Also, the positive moment increased significantly in those spans. So that's why it's important to see how the moments are changing and to check the structure for every stage to make sure the stresses are sound and safe and we don't have problems with the girders. And then later on, when you go ahead and apply the concentrated loads which are applied to counteract or to make sure that we can control the deflections at the tips of those cantilevers. So I think I can see now we are almost 3 p.m. I still have one model to go over it very quickly, but it's a very sophisticated model because it's a cable stayed bridge. But Lucy, do you think I can go over this, or you wanna save it for
I think yeah,
model?
you can definitely go over it.
Okay.
You said it's gonna be not that long-ish.
Yeah, I mean, I can. Yeah, cable stayed bridges is a huge topic. We can never
Yeah, definitely
cover.
go for it.
Yeah, we can never cover that in a session or 10 minutes, but I just want to give the idea of the construction staged analysis, which is what we
Yeah,
are focusing on today only.
definitely.
But
Yep,
there are
go for it.
huge, yeah, thank you. There are huge topics in cable stayed bridges. So this cable stayed bridge is I was working in this project. I've not designed really a cable stayed bridge fully, but I was tasked in this project only with the finite element analysis, which is the interesting part. And I built that model for the construction stages and the final stage of the bridge. So I'm going just to give you the flavor for the dealing with this type of complex structures or bridges. So this is an example of a cable stayed bridge where the two side spans are 75 meters and the inner span is 150 meters. And I know that those numbers really don't sound like the typical span ranges for cable stayed bridges, which are way larger than these spans that I'm mentioning. But for that particular project, that was the case. For some politics, they wanted to have this system as a cable stayed bridge. So the system for that bridge is consisting of, you can see, this is a concrete box girder section, and this bridge is consisting of precast segmental post-tensioned concrete box girder section. So this is a precast segmental section, which means that this superstructure comes in segments, and those segments can be 3 meter long, 5 meter long, as long as they can be transported and lifted and other aspects in the project, but they come in the form of segments, and those segments are erected one by one, and you have some post-tensioning for cables and post-tension bars that erect the piece and keep it in place, and then you go and get the other piece beside it, and the construction progresses this way. So this bridge also was using the balanced cantilever construction method as the construction technique of the bridge, which means that we start first with the construction of those two pylons, which are the large towers that are supporting the bridge. And basically you have a derrick, or you have a carriage that is on the top of the bridge here, and this derrick lifts a segment that's coming from a barge or a ship that's supporting this segment all the way here, and then the derrick lifts it all the way up, it erects it, and then we post tension some bars and some cables to keep the segment in place, and we finish the segment on this side and then switch to the other side. So that's why they call it balanced cantilever, because all the time you erect one segment at one side, and then you go to the other side, erect the other segment, and that's how the construction progresses. Definitely, building a model like this, you need to build the final stage first, which means that you build the entire model with all the elements, including the deck elements, the pylons, the piles, the cables, the pre-stressing bars, everything. And then later on, you start designing your construction stages. So this model here has 52 phases of construction, different construction stages here, starting from the first phase when you have the two pylons constructed in place. And you can see here, I have created groups in a way that I put all the elements that will appear in phase number 1 in one group and the elements that will appear in phase number 2. So let me go back to the base view here. You can see clearly if I hit on phase number 1, those are the elements. I think maybe just make it clear like this. Yeah. Phase number 1, you go to phase number 2, those are the elements that are going to be constructed in this phase. Phase number 3, the other side, because that's balanced cantilever construction. Phase number 4, we have 2 segments. Phase number 5, 2 segments. Phase number 6, and a cable or a pretension cable that's placed in this phase, and so on and so forth. So you start putting all your structural groups this way until you cover all the stages of the bridge. Also, the boundary condition needs to be defined into groups based on each group will be activated in which phase. Like, for example, this group is in phase 6, this is in 10, this is in 14, and so on and so forth. Also, all the load groups the same way. You have a group for the self weight of the structure, the superimposed dead load, the pre-stressing, and you can see here the pre-stressing on structures like these is constructed, of course, inside the phases, which means that you, in each phase, you are going to tension or to pull or post-tension some of the cables only that are required to be tensioned in this phase. That's why I broke the post-tensioned cables here by phase. You can see phase 3, 4, those are the 2 cables in phase number 3, 4, 5, and so on and so forth. Also, we have post-tension bars beside the post-tension cables as well. So they are defined the same way and split in the phases. And we also have the pre-tension force that is in the cable stays the same way. So that's how you define your groups for everything. Also, one of the important loads that needs to be included in those types of bridges is the Derrick weight, which is the weight of the carriage that's on top of the bridge. And basically you move this weight from one side to the other all the time as the construction progresses. We have also the weight of this derrick needs to be one time considered for the case when it's unloaded, like it doesn't have, it's not lifting the segment or carrying the segment that needs to be erected, and one time when it's loaded, which means that it's carrying the segment. So I'm just going to go quickly on the construction phases, very quick like this, and maybe we can talk about this in more details in future session or something. So you can see here, this is phase number 1. We have the derrick positioned at this location, and it's carrying one segment from this side and the other segment from the other side. And then you see the switch of the derrick, because there are 2 derricks here, one that's having a larger load and the other having a smaller load. And the reason for this, because now we installed this first segment here, so we switched to the other side. So this means that derrick is loading a segment here from the barge and coming all the way up to erected, while this derrick is staying empty on the bridge because it's not carrying the segment. That's why you can see the difference in the load, but still the weight needs to be included because the derrick is still on the bridge. So also, if you want me, I can also activate or show in the view, sorry, show in the view the tendon profile. So you can see also how the pre-stressing is also applied incrementally or applied in the phases as it goes. So that's how it's tensioned, which means that each cable is tensioned in a different phase. So that is how you progress, and one stage that you put the stays on and pre-tension them and proceed until all the phases are completed to the middle of the bridge, where you cast your last segment, which is the closure segment in the middle. And of course, models like these needs to include the geometrical nonlinearity effects. It needs to include the long-term time-dependent properties for the material, like creep and shrinkage effects. This way you can get estimates, good estimates for the deflections, but all of those are different or they're independent topics that need to be covered independently outside the construction staged analysis. I think that's all what I have today. For today, I enjoyed this session very much, and I will transfer the to Lucy. You can take over from this point.
Thank you so much, Amir. That was honestly really amazing. We have a couple of questions. Give me 1 second and I will pull them up. Okay. Okay. All right, so far we have 3 questions. I think there's some still coming in, but we'll update it in a bit. But yeah, so the first question we have is from Kelly, and she asked, can you please explain the difference between construction stage and an additional step within the construction stage?
Yeah, I mean, these additional steps are, I think, are meant to include some activation, for example, of a load or activation of some change in material condition or something on the same stage. So this means that this applies to that stage with the deformed structure, with the same deformed shape of the structure and everything, just including an additional stage before before the software goes to the next stage and starts the analysis from the deformed stage of the previous at the previous stage, or what it ended up with. So I have not used that many times in the past, this additional step. But I can also maybe investigate this more, and you can easily maybe email me or something. I can get you some more details on this additional steps if you want to.
Yep, I think that would be awesome. Kelly, yeah, if you want additional information, please feel free to let us know and we will connect you to Amir. Okay, moving on to the next question we have for the plate element / U-girder composite section. How do you feel the self-weight of the deck on the beams at non-composite stage? Are they applied as a linear load or are they applied as a superimposed plane / surface load on dummy deck plate in parentheses plates? I mean elements, sorry.
Yeah, so the thing is that there are two basic differences between those two cases. So for myself, I always like to apply the self-weight of the deck, the weight of the fresh concrete of the deck, and the stay-in-place forms and the haunch and the diaphragms as linear loads or uniform distributed loads on the non-composite section of the beam. That's how I like to do it. The issue of applying this load as a plain surface load on the dummy deck elements, yes, we understand that the dummy deck elements do not have weight, so we are not duplicating the weight. But the problem will be that you activated the stiffness of these elements. Those dummy elements still have a stiffness. They don't have weight because the material is having a zero density definition, but it still has the stiffness. So what I worry about that this load is at the end of the day understood by the program that it is acting on the composite section, not on the non-composite section, because of applying it through the dummy deck plate element. And the other thing that I'm not, I don't see the reason for applying it on the dummy deck elements, because we previously know the distribution of the load. We can approximately say that this is by tributary area. Each girder is going to carry center to center of the load or something, so we can easily calculate the load and apply it as a linear load. We don't have to expect a different distribution of the load if we apply it over the deck plates or the dummy elements. So I would rather prefer applying this load as linear load on the elements, on the non-composite beam elements. Yeah, so you want me to proceed with the third question?
Yes, please, Amir. Thank you.
Oh, okay. So how are pre-stressing losses accounted for in the pre-stressed concrete bridge model? So there are two ways to include the pre-stressing losses in the model. So in the definition of the tendons, if you go and define the cross section of the tendons and the radius or the diameter of the strand that you are using, there are some tabs inside that where you can define the different parameters that are used to calculate the losses for the pre-stressing. For example, for the curvature, you will have the friction coefficient, you will have the wobbling effect, you will have the all those different parameters that are used in the equations to calculate or to determine the pre-stressing losses. And you also have the transfer length effect. It's also included in. So that is one way to do it. Or the other way, if it is not really much of significance to you, or you don't worry about it, you can even do this calculation externally using spreadsheets or whatever. Evaluate your losses based on the type of member that you are dealing with, either pre-tension member or post-tension member, and determine the percentage of losses at transfer and at final stage. And you can just easily apply your force or your stress after deducting the loss percentage. So because you definitely, by the end of the day, you define the stress, the initial stress for the cables. So either you define this value as 75% of the ultimate strength, and this means that you are not including the losses and you need to calculate the losses using the software, or rather you can just determine the percentage of losses externally and just deduct it from the initial stress. So this way you are just applying the effective stress at service right away.
Okay, thank you. Sorry for I had technical difficulties before,
Yeah.
but thank you so much. Okay, so then moving on to number 4. So how long was the closure time to replace the damaged girder?
Yeah, so that's a good question. Yeah, I mean, this closure time, I mean, the I-10 was never closed. That's the issue, because the I-10 is a very primary route. So actually the government worked with the contractor to make sure the working time hours was usually at night. And this whole operation of replacing the girder just took a few days in terms of the demolition and taking the floor beams out and replacing the girders. It was a very fast way or expedited way just to make sure to maintain traffic or to keep the I-10 in operation some hours during the days. Honestly, I don't recall exactly this detail at the moment, like what was exactly the closure time or how long it was, but I remember that thing was managed very well.
Okay. And then was there anything to prevent future impact damage to steel girders?
Well, I don't think there was anything in particular applied to protect this from future impact damage. And by the way, the problem of having this kinds of damages, the impact damages, or having trucks hitting bridges is happening every day and all the time in United States. I'm not sure why, if we really follow the clear height requirements that are in the manuals, in the codes, in the transportation design and everything, but it still happens. And there was no, like, I cannot say there are any preventative measures that were really taken on the ground to prevent this type of damage in future. The steel girders were only repaired and put in place and painted just to protect them from corrosion. That's all.
Okay, and then the last question we have today is, can you show the setting for the cable-stayed bridge where you tell the program to consider geometric nonlinearity? If you want for this part, I can give you control so you can share your screen.
Yeah, okay.
1 second. Okay.
Yeah, I think all the analysis options for the cable stayed bridge mainly comes from this window, this one here. This one is basically the construction stage analysis control data. And this window is very important, not only for the geometric nonlinearities, but it also controls many other aspects in the analysis as well. So what I'm sure about that you can choose what your analysis type is going to be, either linear or non-linear, and even if you include the material non-linearity in the model, which is not really typical, but you can easily select that from here. And for the non-linear analysis, you can also include the time-dependent properties. And for each independent stage, I believe this P delta effect is what you are asking about for the geometric nonlinearity, because that's the most important aspect of this type of analysis. So this happens from here, basically from the construction stage analysis window. Yeah, not sure if this answers your question or.
Okay, I think so. Yeah, I don't think there's any more questions. So I
Yes,
think
and this one as well, the nonlinear analysis control. So this one where you also pick the geometric nonlinearity, and there are also different types here for iteration methods or other settings that you can look at. But I think this one also needs to be checked, definitely, the geometric nonlinearity, and you can control the other options, including the P delta effect and other things from here, from the construction staged analysis window.
okay, I think that answered it perfectly. Yoon says, thanks, Amir.
You are welcome.
Yeah, okay. So I think if we don't have any more questions, I guess this concludes our session. Amir, thank you so much. This was
You
such
are
an
welcome.
amazing session. I know everybody here truly enjoyed it. Um, yeah, we're going to put this up later on our Midas Expert Network resource page. And anybody who wants to can go ahead and look it over again. And Amir, I will follow up with you soon. And yeah, thank you everybody so much for taking time today
For
to be
those
with
who
us.
are saying thank you to Amir in the question box and also in the follow-up survey, we'll make sure to deliver this to Amir.
Yes, definitely. Absolutely.
Thank
Amir,
you.
thank you so much.
You are welcome. Thank you very much.
Okay, have a great day, everybody.
Thank you, Amir. Have a great
Thanks.
day, everyone.
Thanks to everyone. Thank you.